All right, today we're going to be talking about parts of similar triangles. Yes, sir. Oh, okay. Parts of similar triangles. And we got a couple of theorems that I want you to get in your notes. All right, we got three theorems here to get in your notes, and they are all going to start with. No, we're going to do them individually. Never mind. If two triangles are similar. The lengths of the corresponding altitudes are proportional to the lengths of the corresponding sides. So in these two triangles here, an altitude of a triangle, it connects a vertex to an opposite side and it intersects at 90 degrees. All right, this is an altitude right here, AD. Goes from a vertex to the opposite side at 90 degrees. So what we're going to say is that if triangle ABC, this symbol right here, this means similar. Similar. Now the triangles aren't congruent. All right, congruent means that they're the same. We're talking about similar triangles here. So the one on the right could be bigger than the one on the left, or vice versa. So if triangle ABC is similar to triangle FGH, then here's what's true. AD over FJ, AD divided by FJ is equal to AB over FG. If two triangles are similar, the lengths of the corresponding altitudes, these are altitudes in both triangles. F to J is an altitude. It connects a vertex to the opposite side and it intersects at 90 degrees. A to D is an altitude. vertex to the opposite side intersects at 90 degrees. So AD over FJ is equal to side AB over side FG. Now there's another proportion we can write. What's another proportion that we can write here? AD over FJ. What else could that be equal to? What are two other corresponding sides? AC and FH. Very good. All right. So if for some reason you weren't given side AB or side FG, that's not the only proportion that you have to use. Okay, there's one more we can write here. Let's say AD over FJ. What else could AD divided by FJ be equal to? CB over HG. Very good. Okay. Keep in mind that when you write your first proportion, if your altitude is from the triangle on the left and it's in the numerator, then the corresponding side you pick has to be from the triangle on the left and it has to go in the numerator. Got that, Carolina? Good, good. So let's do one of these. Let's say that we got a 16 and a 20 right here. 16 and 20. X and 15. All right, so in order to solve for X, we would write a proportion. We would say that X over 16 is equal to 15 over 20. And when you're solving a proportion, you crisscross multiply. All right, you crisscross multiply. So we take 20 times X. We get 20X equal to 16 times 15, 240. If we divide both sides by 20, then our X is equal to 12. X is equal to 12. Oh, the 16 got multiplied by 15. The 16 times the 15, that's equal to the 240. And the 20 times the X, that's equal to your 20X. Good? If two triangles are similar, the length of corresponding angle bisectors are proportional to the lengths of corresponding sides. So now this is the same rule that we just discussed, but instead of altitudes, it's related to angle bisectors. So if we got a triangle on the left here, ABC, and we got a segment coming out of angle A, and it goes from a vertex to the middle of an opposite side. No, I take that back. It comes out of a vertex and it just splits the vertex in half. It looks like this. AD is an angle bisector. It's a segment that splits angle A into two equal angles. And then if we got a triangle over here on the right, DEF, and it's got a segment coming out of D that splits angle D in half. And if segment DG splits angle D in half, then it's an angle bisector. And here's what we got. We've got another case of if triangle ABC is similar to triangle DEF, then AD over AB is equal to DG over DE. And everything that we just talked about in the previous theorem applies. AD over, I said AD over AB. You know, you can do that as well. I didn't really write that totally correct, but it's not incorrect. Did you see the difference what I did there that time? I took the altitude, I took the angle bisector and I put it over the side to the right of it. And I made it equal to the angle bisector over the side to the right of it. You can do that as well, okay? That proportion will work as well. The way the theorem is written, though, technically correct, it would be AD. It's not really incorrect. So AD over DG equals AB over DE. Can you guys see why these two proportions are the same as each other? Right? In both proportions, in the upper left, you have an AD, and in the bottom right, you have a DE. Agreed? You got an AD up here and a DE. You got an AD and a DE. Well, in this proportion on the left, you got an AB in the denominator on the left and a DG in the numerator on the right. And then over here on the right, you've got the same thing but opposite, don't you? But aren't you going to be multiplying anyway to solve? And in both cases, isn't it going to be AB times DG? And over here, it's still going to be AB times DG, right? So you can write the proportions that way as well. All right, let's get one more theorem in your notes here. And it's going to start with if two triangles are similar. the lengths of corresponding medians are proportional to the lengths of corresponding sides. All right, so now we're talking about medians. We've talked about altitudes, angle bisectors, and now we're talking about medians. All right, and here's what a median does. If we got a triangle on the left, we got another ABC. And a median goes from a vertex to the middle of the opposite side. Vertex to the middle of the opposite side. And you know that it goes to the middle of the opposite side because you'll see a tick mark. So in this case, AD is a median. All right? AD is a median. It goes from a vertex to the middle of the opposite side. So if you've got another littler triangle over here, DEF, and there's a segment coming out of D, and it goes from D to the middle of the opposite side. DG would be called a median. And the same rule is going to apply. All right, AD over DG is going to be equal to AB over DE. AD over DG is also equal to AC over what? DF, good. And AD over DG is also equal to CB over FE. And that's all if ABC is similar to DEF. Anybody have any questions about any of those theorems? Okay, then let's take a look at triangle angle bisector. An angle bisector in a triangle. Separates the opposite sides. Into two segments that are proportional to the lengths of the other two sides. Angle bisector here is what we're talking about. Angle bisector. Separates the opposite side into two segments that are proportional to the lengths of the other two sides. So let's take a look here at triangle JKL. And let's put an angle bisector in here. It comes out of J. And if it's an angle bisector, it comes out of J and it splits J in half. So it does this. Call this M. So we're going to say that if JM is an angle bisector, then KM over LM, okay? KM over LM is going to be equal to KJ over LJ. Y'all see it? If J to M is an angle bisector, then this piece over this piece is going to equal this piece over this piece, and vice versa. Okay? If that's an angle bisector, you can also say this, that if JM is an angle bisector, then JK over KM will be equal to JL over LM. All right? Angle bisector separates opposite side into two segments that are proportional to the lengths of the other two sides. So let's take a look at a couple of examples here. We've got this triangle. SQR. We've got an angle bisector coming out of R. You know it's an angle bisector if these two angles have the arc mark on them. Here's the dimensions that are given. S to R is 14. I'm guessing that's a 6. Yeah, it looks like a 6. Q to R is 6. S to Q, that's 18. And T to Q is equal to X. So look what's going on here. Angle bisector. R to T is an angle bisector. So our proportion is going to look like this. What we're missing here, all right, this angle bisector splits these sides proportionally so that this piece, this TQ over 6, is equal to this piece over this piece. All right, so our first ratio is going to be X over 6 is equal to, all right, we did X right here over 6 right here. The next piece we need to use is ST. But ST doesn't have a dimension, does it? But do you see this overall dimension? This 18? And T to Q is equal to X. That makes S to T is going to be equal to 18 minus X. All right, so if our X was in the numerator, this 18 minus X needs to be in the numerator. And it goes over this 14, which is SR. So now when you guys crisscross multiply, you have to do the distributive property. So I'm going to do the X times 14 first. We're going to get 14X equal to, then we got 6 times 18 minus X. So now this 14X is going to be equal to 6 times 18. What is 6 times 18? That's 108. Minus, you got your 6 times 18, and then you got your 6 times negative X, and that's minus 6X. Everybody see that set up? All right, so now we're going to add 6X to each side. And we get a 20X equals a 108, and we can divide by 20. So our X is equal to 5.4. Does that make sense to everybody? Let's do one more of those. Let's say we got this right here. All right, again, you've got an angle bisector because it's got arc marks telling you that both angles are congruent to each other. So we need this piece right here. We need this green piece. What's the length of that green piece going to be equal to? Good. 20 minus x. What's my proportion going to be to solve for x here? All right, you're going to do x over 14. Okay. X over 14 equals 20 minus x over 11. Good. Everybody see that? All right, so we're going to crisscross multiply. 11 times x is 11x. And then we got 14 times 20 minus x. So 11x equals 14 times 20 is probably 280 minus 14x. So add 14x to each side. And 25x equals 280. And then divide both sides by 25. So 280 divided by 25, 11.2. Any questions from any of those theorems or examples we did today? All right, here's your practice problems for today. Your practice is page 91 in the workbook, 1 through 8. And then page 92 in the workbook, 1 through 7. Be sure you check focus for homework. Any questions from anybody Zooming? All right, you're free to exit the meeting if you don't have any questions. At this time, I'm going to end this meeting.